actually 0th coefficient and 64th coefficient. So 64th coefficient, when it reach, the value for Mach 1 is 294th clock. So 294th clock, the 8 kilohertz, and 590 clock, 16 kilohertz will be in working. So here 590 is plus 128 actually. So after this, log computation will start after completing the entire S of n calculation. So once the S of n calculation is completed, for the first MEL bank for the 8 kilohertz, it has only 3 non-zero coefficients. So after 294, within 3 clock cycle, we'll get the first value. So 296 is the first clock period where we'll get the first log of n. So similarly for the clock 16 kilohertz, 4 non-zero coefficients are there. So for 592, 594, we'll get the first coefficient for the log. So, but the last coefficient we'll get only when the Mach 1 last bank when it completes. So the last bank after it completes, we'll get around 360 for the last bank, and here 721 for the last bank. So for the cost computation, actually we are not going to do any computation. Whenever a log value is there, we can directly read it. So it doesn't need any extra clock cycle. So cost computation also we are considering it the same clock count. It means it doesn't have any clock count. With the same clock period, the data will be available. That is the only thing we are considering. So Mach 2 has to start operation for the 342th clock cycle. Why in the sense, when we want to compute the C of n, we need entire 20 coefficients of the S of n. So that means each MEL filter bank energy computed value. So the last filter bank value actually has 20 non-zero coefficients. Since it has a 20 non-zero coefficients, from 361, 20, if you go back, 342. So at 342, 19 coefficients are available. So during that time, we can start our first computation. So if you start the first computation at 342 till 361, the Mach 2, that means C of n computation, sorry, 371 to 382, which is actually 20 clock cycle. Sorry, 342, 361, which is actually 20 clock cycle for the C of n calculation. Similarly for the 703 to 722, which is actually C of n computation for the 16 kilohertz. But the starting operation is 342, but we'll get the first feature vector at 371 clock cycle for the 8 kilohertz and 732nd clock cycle for the 16 kilohertz. So from 371 clock cycle at continuous instance, we'll keep on get the upcoming or next feature vector for the continuous frame without any gap other than the ideal time. So even in the ideal time, the last feature vector will be maintained as a previous value and the present value. So once the ideal time crashed and the next frame it start coming, the next feature vector it will start come. So the latency for the 8 kilohertz is 382 and latency for the 16 kilohertz is 743 clock cycle. But this latency is not based on the pipeline. This is due to the memory modules present within this. So it's not only the memory module and the requirement to read the input. So each and every stage we can't able to read the inputs in order 0, 1, 2, 3. We have to read in random order and we need to wait for some other that means later future stages of input to process the previous, that means n minus x stage of input. Due to this, the latency is too much high for the entire design, but the advantage after this much latency, in continuously each and every clock we'll get one feature vector as a output. So the write count and read count, it's actually following a mathematical functionality. So if you have a non-overlapping sample of A for the 8 kilohertz or B for the 16 kilohertz, then all the odd frames will start at 2 into x into A to 2 into x into A plus 199, where x is from 0 to n. Similarly for the B, 2xb to 2xb plus 399, and for the even frame, it's 2x plus 1 A to 2x plus 1 into A plus 199, and for the 16 kilohertz, 2x plus 1 B to 2x plus 1 B plus 399. This is for the write count. Similarly, for read count also, it has following the some mathematical equation, which is actually 2xa plus 192 as reading sample of first reading sample, and the last reading sample will be 2xa plus 255. Similarly, for the 16 kilohertz, 2xp plus 384 to 2xb plus 511. Similarly, for the even frame, 2x plus 1 into a plus 192 to 2x plus 1 into a plus 255. Similarly, for the 16 kilohertz, 2x plus 1 into b plus 384 to 2x plus 1 into b plus 511. So, since we have mathematical functionality inside it, the entire architecture, we can able to build it with the configurable design. So, results and discussion. For the version 1, whatever we did, for the ASIC synthesized with the 45 nanometer technology, we got the result of delay, power and area. Similarly, for the version 2, we have the FPGA simulation results. So, this is for the complex adder, so which is used in the Mac and the Butterfly of the FFT. Also the log computation. This is a complex multiplier which is used in the FFT, and the floating point adder, that means it's not exactly the IEEE standard format of floating point. It's a floating point format which we used with some exponent bit and some Mantis bit. So this is the complex floating point multiplier. So floating point Mac result, and then the FFT with the DIT architecture. So logarithmic computations, X4. So the entire design is optimized with less memories, that means minimal memories with less number of clock cycle, and it can be configured with higher number of sampling frequency also. Since the entire design is followed only based on the clock counter, so even in future, if the sampling frequency increases more than 16 kilohertz, still the same design can be opted or same design can be applicable unless the memory speed is exactly equal to the sampling speed. So this design, the maximum delay will goes for the memory, not for the logical functions. So if the memory speed and the sampling speed, if both are equal, this algorithm will be perfectly fine and it will be applicable for the entire design.